Okay, recording. All right, so we're looking at populations and samples. A parameter is some measurable quantity related to population, like an average or a percent. Normally, we can't get the whole population, so we have to settle for a sample. In a sample, when we make a calculation, the calculation is called a statistic. So different sample statistics that we've already looked at are average, which is also known as the mean, median. We get to look at standard deviation recently. Standard. We have percentiles and quartiles and just regular old percents. So we've been doing these descriptive statistics, and the point of doing these descriptive statistics are we can't get a hold of the whole population. So we use the samples to try and guess what's happening with the population. Now, oops, wrong button. In order to do that, we have to actually get a sample. So how to get a good sample. In order to do this, we do what's called random sampling. And the random part is super important. So I couldn't just take the 11 people in our class and get your ages and say, hey, the average age of a person that lives in the United States is this, because you guys are a biased sample. You were too convenient for me to grab. You were all here for a reason. Students tend to be younger. So grabbing this class and using some numbers from this class would not be a good prediction of college students in general, college students at BMCC, people in the United States, people in Umatilla County, people in Oregon, just because you guys aren't a good random sample. So randomness and sampling is super important. So that's one thing we'll get to here. The other thing we want is a representative sample. So if I were asked to do some kind of survey about people in Oregon and I only got people from, say, Umatilla and Morrow counties, that would not be a sample that's representative of the whole state. Or if I went to Portland and just grabbed people from Portland, that would not be representative of the whole state. So somehow we need to make sure our random techniques for sampling get a variety of different people in there. Now, we're not always sampling people. It could be fish in a pond, it could be squirrels or cats, or the length of a bolt manufactured somewhere, or the quality of an iPhone or a cup of coffee, right? Whenever we do our sampling, we want it to be representative. So representative means like the population. So if my population were, say, 60% female, then I want my sample to be 60% female. If my population had the majority of people aged 25 to 35, then I would want to make sure my sample had a majority of people that were 25 to 35. So there's all different kinds of considerations you have to make about making that random sample. So the first kind of random sample one can take is what's called a simple random sample. And it's kind of simple. The idea behind a simple random sample is kind of like choosing cards from a deck. You shuffle the deck, you look at the card, you make a note what it is, you put the card back in, you reshuffle it, and you pick a new card. Each time a particular card has a 1 in 52 chance of getting picked. So with a simple random sample, each individual has the same chance of being picked. And there's kind of another requirement that just happens in there. Each group of a certain size has the same chance of being picked as another group of the same size. Each group of size n has same chance as any other group. Of size n. So let's suppose someone told me I needed to sample Oregonians and I should sample 500 people. So I have to design the sample in such a way that any group of 500 people I pick is just as likely to be picked as some different group of 500 people. And so that's kind of a consequence of saying I want 500 people and I want it to be simply random. Now the problem with a simple random sample is in order to do it, you have to have a list of every individual that you're sampling. And often that list is hard to get. So a simple random sample is often hard to implement. If I have the list, then I just need some way to generate individuals randomly. So different ways to do that. There are random number generators out there. There's a place called random.org, which is one of the best ones out there. And here it says off to the side, true random number generator. And they say, what's the fuss about true randomness? They have a lot you can read about that, but it is a big deal. And this right here will generate a random number between 1 and 100. So if I had a list of 100 people, I could then pick one of them randomly. Now there's 11 people in our class, so I could generate somebody from 1 to 11, and then just grab the second person on my roster and say, okay, you were randomly selected to get some peanut M&Ms. Woo! And true randomness is a problem. It is hard to do. Humans aren't very good at it, it turns out. So just a quick note about randomness. Number one, humans are not good random number generators. We are very biased in our choices. So if you think that you're going to do a random sample by just thinking up, maybe you have 20 things you have to sample out of 100, and you just randomly pick 20 numbers from 1 to 100 in your head. You're probably going to have some bias in the way your brain goes about doing that, and it's not necessarily going to be a good random sample. So again, we shouldn't try to do that. We're not good at it. There's tons of studies that show that over and over again. So we have to usually rely on some computer simulations. And a lot of research and development has gone into trying to make random number generators. And I remember years ago, Microsoft Office, Microsoft Excel has a random number generator in it, just like Google Sheets does. So let me bring that up. Sure, I'll put this page, move this up a bit. So they have, usually spreadsheets have two functions for generating random numbers. One is just called rand, and it returns a number between 0 and 1, which means 0 is inclusive, 1 is exclusive. So you could get 0, but you will not get 1. And so you just close the parentheses with nothing in it and hit enter. And it turns out anytime you do something new on the screen, it regenerates that number. And you can fill that down and generate 10 random numbers. But the weird thing about the random number generator is every time something changes on the screen, then the random numbers are regenerated. Okay? Microsoft in their spreadsheet have had many different versions of their computerized. Hey Josie, good to see you. I'm glad you could join us. We're playing around with random numbers right now. When one of their earlier versions of the random number generator accidentally generated more numbers between 0 and 1/2 than it did above 1/2. So there was some bias to it, and some researchers figured it out that there was a problem with it, and Microsoft spent a lot of money in a couple of years trying to fix it. And this company called random.org, well, they have a website called random.org, I forgot the name of the company, but they've put years and years into research and development and making random numbers. And you're like, well, who cares? Well, it turns out there's a lot of reasons we need random numbers in terms of selection in a lot of different areas. it is a big deal in computer work. It's been a big deal for a long time. So I get this random number between 0 and 1 is the rand function. So let's make a note that right up here, I typed the rand function. Another generator they have for random numbers generates a random whole number, or random integer, and that one's called rand between. You pick a starting point and an ending point for that. So kind of like the start comma end, the random.org, where they say, okay, here's the smallest number we might generate, here's the biggest one, blow that up, generate, and then it picks a new number. Could be 1, could be 11, you never know what's going to happen. So it's kind of like rolling the dice. And it turns out it's very hard writing a computer program to do that or to try and do that in your head. So humans aren't good random number generators. The rand between, I just start typing equals rand, and then I pick, oh, I forgot they have rand array too. Rand between says, what's the lowest number you want? And I could say 1. What's the highest number you want? And I could say 11. And then I hit enter and it says, okay, 6 is your random number. And if I fill that down, I've just generated 9 random numbers between 1 and 11. And again, remember, anytime you change something on the sheet, these numbers are going to recalculate. So if I say hello over here, I now have a new list of random decimals and a new list of random whole numbers. So a spreadsheet's a good way to generate random numbers, either whole numbers or decimals, to use to make some kind of simulation. Random.org is a good thing. Some other examples of stuff that aren't good ideas for random number generators. Let's see, something else that's not, that people sometimes think is. This is a bad idea. Closing your eyes and pointing something. Turns out that's quite biased. That's slightly worse than throwing a dart at something. Some people have skills with darts. They can put it in a pretty good spot. Other people can't even hit the target. So that's a bad idea, right? Don't do this. Humans are not good at it. Another thing that is a good idea, as long as it's done right, is writing words on paper. So write individuals on paper, and then you mix them up and draw from some kind of a container maybe, without looking. So there's a couple of elements of pseudo-randomness going on here. One is I would want the paper to be uniform. 2, I'd want to mix them up. And 3, I would want to have some kind of container that I draw from without looking. Okay, so the uniform size, the mixing, and then the random choice together make a pretty good random generation system. So that can be off. But there are problems with that too. And there was a draft done in the late 1960s related to the Vietnam War, I believe it was, where they screwed this idea up very badly. They didn't do it well, and it turns out their selections were biased. Not every young man had the same choice of being selected as every other because they screwed up the mixing and the container thing. So we've been trying for years and years and years to make computers do this for us, and we're getting better and better at it. So really with computers, they're called pseudo-random number generators because it turns out we haven't figured out how to do true randomness yet. All right, so some other things we need to talk about. So random stuff. Why do we care about random stuff? Again, because we want to have good samples. In order to have a good sample, we need the idea of representative, and we need some randomness to be in there. Now, just truly random stuff isn't necessarily the best idea. We usually have to mix it up with some other strategies. One mentioned in the book is called a stratified random sample. And with a stratified random sample, what you do is you break up the population into groups. So you got this group 1, and you got this group 2, and you got this group 3, and so on. And you might have a lot of groups, so there could be, you know, like 20 of them. Let's suppose I have 10 of them. And then what you want to do is randomly select from each group. So then we select proportionately from each group. Okay, so what do I mean by proportionately? Well, let's just say that group 3 is the biggest group. So maybe group 3 represents 20% of the population, and group 2 is only like 10% of the population. Group 1 was only like 5% of the population. Maybe group 10 was 10%, and there was some other ones in between. So altogether, we account for 100% of the population. Then when we do our sample, we want in the sample group 2 to have about 5% of the people in the sample, and group 2 to have 10% in the sample, and group 3 to have 20% of the sample. So for example, let's suppose I said my sample size was 20. Then from group 1, I would only want to take one person, because 1 out of 20 is 5%. From group 2, I would want to take 2 people, because 2 out of 20 is 10%. From group 3, I would want to take 4 people, because 4 out of 20 would give me 20%. So again, that would be trying to choose proportionately based on percentages we know about a population. Sometimes the stratification could be male versus female, and we want half males and half females. The stratification could be age groups. The stratification could be ethnicity. There's lots of reasons we want to stratify by a specific attribute to make sure we're getting a sufficient number from each of those subgroups of the population. So stratified random sampling. We split the population up into some groups based on a good reason. And then from each group, we select randomly. So I would randomly select however many I need from group 1 and randomly select from group 2 and so on. One problem with stratification is you often don't know those actual percentages in the population. You at least have to have a guess in order to try to get a representative stratified random sample. So the book mentions that one. There's a couple of homework problems related to it. Another type that's not in the book, but I'll just mention it to kind of give you another example, is what's called a clustered sample. Clustered random sample. And clustered random sampling is something like stratified. And you've been in a clustered random sample before, most likely. So for example, every year the college has to take part in this national survey for college students. And the way that survey works is they pick certain colleges to participate, and then in that college, they randomly select a few classes, and every student in that class has to take the survey. So usually one of my classes gets selected every year, every other year that we do it. So that would be clustered by classes. So some students would take the survey, but some wouldn't because they weren't in one of the selected classes. Another example of when clusters come up is maybe you have this town, and the town has different neighborhoods in it. So let's say here's a breakdown of the neighborhoods in this town. A clustered random sample would be to randomly pick some of these neighborhoods, and then we survey every single person in the selected neighborhoods, and we don't worry about the other neighborhoods. Okay? Whereas a stratified random sample, you would have to get a proportional amount from each and every single neighborhood. Okay, so if there's more people in this neighborhood than that one, then there should be more people from this neighborhood in a stratified sample. So a clustered random sample is a different way of using groupings to make a sample happen. And there are tons of other sampling techniques out there. There are whole classes in sampling techniques. We're just scratching the surface on this. So once we have a good random sample, then we do things with it. Like what? Well, we spent the last 2 weeks doing stuff like making histograms and calculating summary statistics. So let's take a look at some of the things we've done before. Here is some data I acquired about birth weights from a particular hospital in Pennsylvania over time. How many do I have here? This group has 100 birth weights in it, and these are randomly selected from a group of like 3,000 birth weights. I calculated the average birth weight to be about 3 kilograms, which is what, almost 6 pounds. And I got a standard deviation of 632 grams and a bunch of other stuff that we've talked about in terms of statistics. Now I can make a histogram of it. So here's a histogram. And what are some things you can tell me about the shape of this graph here? If somebody could come talk to me, that'd be great. I've been talking for a while. Nobody wants to talk to me. I'm so lonely, you guys. Come on, help me out.
The graph kind of makes it look like once you hit about in between the 2,500 and 3,000 grams, right? Is that what it's showing? That's when it starts to rise and spike, and then it really like hits the high in between 3,000 and 3,500.
Yeah.
That's like where the kind of the weights average out a little bit, it looks like.
Yeah, and notice, excellent observation, notice that my mean of 3,200 is right in the middle of this big tower here. And that usually happens in a histogram. So a histogram is a picture of the way the data is kind of grouped together. And we call that a distribution, right? And distribute means kind of like spread out. How do you distribute stuff? How do you spread stuff out? And so this just shows that, hey, most birth weights were between 3,000 grams and 3,500 grams. And then if we spread it a little bit further, we could say, yeah, like maybe 90% of the birth weights are between 2,500 and 4,000 grams, so between 2.5 kilograms and 4 kilograms. There's a few babies that are born pretty darn big, like almost 5 kilograms. And there's also a few babies that have super low birth weights. So when we look at a distribution like this, ignoring these low ones over here, this looks pretty symmetric, doesn't it? It's got this symmetric hump going on there, but we have a tail to the left, and the right does not have a matching tail. So it's not completely symmetric. When we talk about this data set being skewed, and hopefully you read about skew in the book, the tail identifies the skew. Now, there are ways to calculate skewness. There's a few different formulas. We're not going to go over those formulas. We're just going to make a histogram and look at the histogram and say, is there a tail? If the answer is, yeah, it looks like there's a tail to the left, then we would say this data is skewed left. Okay. Let's look at another example. Here, I went to the Oregon Health Authority website to see what's going on. And let's see, this particular data set is from today. So I grabbed today's information from the Oregon Health Authority website, and they had this age group table about deaths and people that were hospitalized and the actual number of cases. And I turned that into a graphic here. So here's a histogram as of 4/20 today of the total number of cases that have happened this year for COVID-19. So I believe we started reporting cases in February, is that right? Early February in Oregon. And so this includes those early cases. So this isn't current cases, active cases, because some of these people have healed from COVID-19, and a small group, unfortunately, has passed away. And they're all still counted here. Now this right here, I don't know if it has a tail. It turns out there was one case that we weren't sure the age of that was listed in their table. And compared to these others numbers, you can't even see the one here. Does this look like it has a tail, or would you say no tail? Anybody?
I don't think that it really has that much of a tail. It kind of looks like it drops off on either side.
Mm-hmm.
So I don't think it really, goes to one side more than the other.
Yeah, usually I'm looking with a tail. I'm like, oh, this one over here. I'm looking for more than one group that's small off to one side, but not the other. And I'm not really seeing that here. So for this data set here, what I would say, it is relatively not uniform, it is relatively symmetric, right? There's a middle of it here, and it's about the same on one side as it is the other. Now this one groups 0 to 19, 20 to 29, 30 to 39, and so on. If I chose a different grouping for ages, this might look a little bit different. So a histogram depends on the groupings that you made, even on the same data set. So this is relatively symmetric. Can't really tell a skewness. Another way a rough guess of skewness, so let me just write this down. Page. So skew of a distribution and a distribution is just a graph of a histogram of some numbers. One test is the tail. Tail is the skew. So my first data set, if I were to kind of smooth it out, had a tail on that side, and then it just kind of dropped down on that side. So I would say this one here has a left tail. So this would be left skewed, or skewed left. If the data, on the other hand, had kind of a hump on one side and then kind of petered off on the other side like that, this has a right tail. So we would say it's skewed right. And then sometimes it's in the middle and it's hard to tell. And that's just a whole nother story. In a situation like this, what we would find usually is that the mean would be to the left of the median. And this side over here would be the reverse of that. The median would be about over here, and the mean would be a little on the other side. Okay. Does that always happen with skewed left data? The answer is no, but more often than not, it does. So if it's skewed left, I would expect the mean to be less than the median. And if it's skewed right, I would expect the mean to be greater than the median. And the reason for that is the median doesn't care how big the biggest number is. It just knows it's the number in the middle when you put them in order. The mean, however, you have to add up every number and then divide by how many. So if there's more numbers way out here, it's going to make the mean bigger compared to the other numbers in the group. So a mean is distorted by outliers. A median is not. It's less likely to be distorted. Josie, do you have a question? Can I slow down? I just saw that note. Was that about the skew that you asked? The mean versus the median. Sure. I am recording this. It'll get posted in the YouTube playlist I have on our website. So the book talks about skew. It's in a couple examples in the book. Sometimes there is no skew. So often we have symmetric distributions. And there's all kinds of different symmetry. The classic ones are like a bell-shaped symmetry. Oops, too many P's. Where the middle is the average. And if it's symmetric, then the median and the average are going to be pretty much the same number. We can have other kinds of symmetry. So there are sets that go up and then they go down, then they go up again. So there could be symmetry in this case, where these two humps are the same size and shape, just on opposite sides of the middle. So maybe the mean and the median line up. So this would be called a bimodal distribution. And mode, remember, is the most frequently occurring. So here we have two groups of numbers that occur most frequently, because these are the same size there. And distribution refers to the shape of a histogram, and they're just infinitely many shapes. Sometimes they're skewed, sometimes they're not. Sometimes they're symmetric, sometimes they're not. Sometimes they're just crazy wiggly. A bell-shaped one that we're going to spend a bit of time on in the reading is an example of a bell shape. There's many bell-shaped distributions, but one of them is called normal. And it kind of got a bad name because we think normal is common, but it turns out it's not all that common. But it is used in a lot of different places in statistics. So we're going to look at a normal distribution next. All right, so I'm going to steal a prettier picture of it. So on our course week 3, videos and more, I have a link to other resources, the StatKey normal distribution calculator and grapher, which you can get to there, or just by searching for StatKey. And I've showed StatKey in a couple of my other videos. So I'm going to look at the theoretical distribution normal. That's what I linked to this week. So this is my symmetric bell-shaped curve here. And this one seems a little pointy just because of the scale that was chosen here. Here we're only going up to 0.4. If I chose to go up to 1 or 2, then this would look flatter. So it's all a matter of scale, whether it's a flatter hump or not. Notice the scale on the side here does not match the scale on the bottom. So this is actually much flatter than it appears. This one has a mean of 0. See that 0 is in the middle. So in this case, 0 is both the mean and the median. And this one has a standard deviation of 1. And we looked at standard deviation before. So I'm going to make a copy of this. And one thing about StatKey, you can't copy pictures here. You got to take screenshots. So I'm going to take a couple versions of this screenshot for fun. And let's see, I can't remember if I started a new page. And I'm going to scale this down just a bit. All right, so I'm going to put another one up here. Desktop, edit parameters. So average body temperature, we believe to be about 98.6. And standard deviation for individual humans is about just under 1 degree Fahrenheit. It's about 0.7 degrees. Unfortunately, the scale they drew here doesn't match the middle. 98.6 should be the middle. So I'm going to redraw a little bit here in just a second. And I don't have control over the scale down there, unfortunately. I'm going to take another screenshot of this for comparison to the other graph. And let's see, current page. And I want these guys to line up as best I can. Not quite. Close enough. All right. You up there. Underneath. Perfect. And let's see, line up their edges. All right. So right down the center, let's make a red line. So draw your best picture like this in your notes. So I'm trying to mark the vertical center here. And that almost goes for the peak. Shift this over just a tiny bit left. Come on, move. There maybe. About the same as before. So this is the middle. And for human body temperature, that middle mean would be 98.6. And so that's that point on the number line, just a touch to the right of 98.5 that it graphed for me. In this graph up here, I think I'll label that one green. This is what's called a standard normal distribution. Standard normal distribution has a mean of 0, notice that's the middle number here, and a standard deviation of 1. This one down here is not standard because it has a different mean. This here is just a normal distribution for human body temperature. This has a mean, x bar, of 98.6 and a standard deviation of about 0.7. So if I go one standard deviation to the right, so let's draw another line. So this would be one standard deviation to the right there. That means from the middle, 98.6, add 0.7. And that would put me at, what, 99.3? And if I went another standard deviation to the right, about right there, if I add another 0.7, 99.3 plus 0.7 puts us at 100 degrees Fahrenheit. And if we went a third standard deviation to the right, just for the heck of it, that would put us right about here, and that would be at 100.7 degrees Fahrenheit. Okay, so notice in the standard normal, this was a 1 right here and a 2 right there. I kind of drew over them, and a 3 right there. So 1, 2, 3 standard deviations to the right. There's nothing special about going to the right. Sometimes going to the left is better. Usually a high temperature is a sign of illness, right? Some people have low temperatures, and that can be a sign of a problem with the body too, if somebody's too cold, some other kind of illness. So we could go the other way. So I could be one standard deviation below average, which would be about here. Oops, try that again. Stay still, please. There we go. So if I take 98.6 minus 0.7, what's that give me? 97.9 would be about here. And if we subtract again, one standard deviation, so we're 2 below average, that should put me about there. So subtracting another 0.7 should be 97.2. It's supposed to be a 9. And third, just for fun to match the other side, if we go 3 standard deviations below average, then let's see, where would that put us? That would put us at 96.5, which kind of matched the graph already. So 96.5. So that's 3 below, -3. When we look at the standard normal, these numbers up here are what are called z-scores. Let's do that green. And a z-score is just some number of standard deviations. Okay, so for example, usually I'm a little below average, and I took my temperature this morning, as I do most times, most days these days. I'm usually a little below average. So my temperature this morning was 97.9. I feel great. Allergies are bugging me, but I'm usually a little cool when one takes my temperature. But again, your temperature changes throughout the day, as does your blood pressure. You know, this is a variable in everybody's body, and it's a variable between people. But on average, most people, on most days, or pretty close to 98.6. If you're too far from this, then something's wrong. Humans function in this range for some reason, and typically most data is going to be within 3 standard deviations. So imagine this curve here is just a lot of little stacks of a histogram, all smoothed out, is basically what the graph is showing here. So if my body temperature measured 97.9 this morning, then I would be 1 standard deviation below average. My z-score for temperature would be -1. And it turns out you can calculate z-scores if you know the mean of the sample or population, if you know the standard deviation of the sample or population, and if you know a person's score. Okay, so let's just test that out for me here. So Gary's temp is 97.9 degrees Fahrenheit this morning. Average is believed to be 98.6. And the standard deviation is believed to be 0.7. So a z-score, remember, is some number of standard deviations. Anybody remember what a standard deviation is?
Yes, was it you take your, let's see if I say this correctly.
Okay.
But you take, is it the mean, or am I wrong?
It's related to the mean. Good start. Excellent.
Okay, so from the mean you do the -2 or +2, or is that completely wrong?
You have the minus right, but it's not a 2. So just what standard deviation is again? It's a measure of average deviation.
Is it the 1.5?
Nope, not the 1.5 either. So those, you guys are thinking about outliers now. So when we're trying to see if somebody's measurement is unusually high or unusually low, we have 2 ways to do that. One rule is using the IQR from a box plot, and the other rule is for using 2 standard deviations. And the book went over that, and I had a video on that. So that's just a slightly different idea. So let's forget about that for a second. Just here, I was just wondering what standard deviation meant. And standard deviation is a measure of average spread from the middle. Measure of average spread from the mean. Okay, so standard deviation just says, hey, you're not average. Are you above average or below average? And it asks that question of every number in the data set. And then it averages out all those differences, because some people are above average and some people are below average. Almost no data value is actually average in a complicated number set. So standard deviation is a measure of how far. So would you agree I'm below average, right? In my temperature. The question is, well, how far below average? So to answer that, we calculate Gary's deviation. And deviation is always some measurement minus the mean. Okay, and so my deviation is I measured 97.9. The actual mean was supposed to be 98.6, right? So my wife's checking, hey, are you sick or not? She takes my temperature, she says, nope, you're 97.9. That's not a fever. And if we do the subtraction here, what we get is -0.7. So it turns out the negative means I'm below, right? And it turns out 0.7 is exactly a standard deviation. So in this case, I am 1 standard deviation below average. Standard, whoa, too many letters. Deviation below average. So below is the negative, and that is 1 standard deviation. So my z-score would be -1. So putting that all together to calculate my z-score, first you have to find my deviation, which means take my measurement subtract the mean, and then say, okay, that difference from average, how many of these standard deviations is that? So we're counting by the number of standard deviations. And so the formula is whatever measurement you're looking at, subtract the mean, and then divide by the standard deviation. And that's how you can calculate a z-score if it's not obvious. So if I look back at my picture here, if somebody had a temperature of 100, what would their z-score be?
A 2?
Yeah, their z-score would be 2 because they're 2 standard deviations above average. And if somebody had a temperature of 100.7, their z-score would be 3 because they're 3 above average. Now, usually measurements aren't exactly 1 standard deviation. So z-scores can be like 1.5 and negative 2.3. There's all kinds of different z-scores out there. But if the data is normally distributed, it turns out there's certain percentages of data that happen within certain boundaries. So I just want to show that quick here. So I'm going to reset this, and then we're out of time for today. I'm going to do a two-tail, and I'm going to set this z-score to -2 and that to +2. So what this picture is showing me here is that if you mark a z-score of -2, so 2 standard deviations below average, and a z-score of +2, so 2 standard deviations above average, then these numbers up here tell you what percents to expect. So this center number right here says that 95.4% of individuals should be between 2 standard deviations of the mean, or within 2 standard deviations of the mean. And only about 2.3% should be less than 2 standard deviations or greater than 2 standard deviations from the mean. And keep in mind, you cannot talk about standard deviations without referencing the mean, because you need the mean to calculate the standard deviation. So deviation is distance from the mean. Standard deviation is an average of all of those distances from the middle. If we were to look at 1 standard deviation above or below average, then we get about 68% of the population in the middle and about 16% in each tail. And your book has some graphs showing these percentages. Now the catch is, this is only if the data is believed to be normally distributed, okay? Do birth weights appear to have that perfect symmetrical graph? The answer is no. If we ignore premature births, then okay, this is pretty darn symmetric right here between 1,500 and 4,500. Okay, so ignoring premature births, birth weights seem to be normally distributed. And what is the mean? Maybe it's 3,200 grams. Maybe the standard deviation is 6,000. This is based on a random sample of 100 birth weights from Pennsylvania. Okay, but maybe there's something weird about babies in Pennsylvania. Right? This is a random sampling of Pennsylvania baby births in the 2010s is when I got this data. Other examples, is this look like a normal distribution? So imagine drawing a smooth line through those numbers. Is it roughly this shape, but squashed a bit? Maybe. I don't think I have enough data to figure that out yet. So there's some caveats here. Normal distributions, we can use them for all kinds of calculations and predictions, but sometimes it's inappropriate to use them. So we should always use them with caution. For example, shooting free throws, if somebody has a 75% chance of getting a free throw in and they try to take 12 shots over and over again, what we would find is most of the time they would get 9 out of 12 in. Sometimes they'd get them all in. Sometimes they'd get all 6 in. There's a little bit of a symmetric bell shape here, but this has quite a tail to the left. If somebody had a perfect 50% free throw rating, then they would have a perfect bell shape to their histogram. But some histograms are just weird. They have humps to them. So there's no guarantee a normal distribution fits every situation. Here's some data I collected about hip replacements. And you say, why would you do that? Somebody else did it, I just found it. And what we find is most hip replacements happen with older people, people over 59. But every once in a while, there's a young person that has some problem and has to get a hip replacement. But it's mostly older people. So we got a skew left here. But this isn't a symmetric bell shape. Okay? So sometimes data is symmetric in bell shapes, sometimes it isn't. Sometimes we can apply normal distributions and sometimes we can't. And the book presents a bunch of situations where we can, and I'll talk more about those next on Wednesday when we meet again. So between now and then, you've got a bunch of stuff to do. This week's going to be a little lighter than the last couple. If you think you need to finish up something from last week, you've got late passes you can apply to stuff. Let me know if you need any help with any of that previous stuff. I have some things to go and grade in here. I'm going to work on that today and tomorrow. Otherwise, if you're done with last week's stuff, you've got the reading that's due today. There's a bunch of videos I posted. Most of them are short. And then there's the homework that's repeatable on distributions. And then there's the activity. And although all of these are set to be due on Saturday, you should probably get them done, start them before that. And that's it for now. Any questions before we part for the day? Seems silence is a no. Okay, then get out and do something. Hopefully you have some time. Miss Olivia, who's super busy, and hey, Josie, we were checking in earlier, just saying something interesting about our week last week. I was saying that I'm going a little stir crazy in this isolation, but I got to celebrate my daughter's 14th birthday last week, which was pretty exciting. Hopefully 14 is going to be better than 13, although 13 wasn't too bad. Every age is challenging. Do you have anything interesting from last week?